Okay, so now we're on question 9, and question 9 says the graph of f of x is equal to ax cubed plus bx squared plus cx minus 5 is drawn below. And then we have e, which is -1 and 0, and g, which is 5 and 0. And these are the x-intercepts of f. The first question is to find the values of a, b, and c. Now, I know many grade 12s actually struggle with when they give these questions where they want you to find the formula of your cubic function. The thing is, you just have to focus on one thing. Focus on the graph and what they gave you. So you look at the graph, and do you see that the only points that they are specifically giving you are x-intercepts? So it means that we're going to use the x-intercept formula. But now you have to use the proper formula. You see, with the x-intercept formula of a cubic function, and remember, because this is a memo, it's also a teaching opportunity, so I will explain in more detail. The thing about it is, let's just briefly explain that. You can have an x-intercept formula where you have 3 roots like that, right? 3 roots, 3 x-intercepts. So with this type of formula, it's going to just look like this. Y is equal to a times x minus x1, meaning root 1, times x minus root 2, times x minus root 3, because these are 3 separate roots. Then you have an x-intercept formula where your graph somewhat does this. Doesn't always have to look like that. It can also look like this, for example. But ultimately what's actually happening is you have roots, but you have 2 roots instead. And the thing about these 2 roots is that one is a turning point and a root at the same time. So this will be the formula for that. Y is equal to a times x minus x1 times x minus x2 squared. So the one that is squared, you can already guess, would be the one that is a turning point and an x-intercept at the same time. Okay, so they gave us x-intercepts. We're going to use one of the x-intercept formulas. And of course, we're going to use this formula. Okay, so let's just establish what is our x1 and x2. Our x2 must be the one that is a turning point and an x-intercept. So x1 and x2. Our x1 would be this one because it's just an x-intercept. That's all, 5. And our x2 is the one that is a turning point and an x-intercept. So let's go ahead and substitute this. So we're going to say y is equal to, we have a times x minus our x1 is the 5, and then times x minus our x2 is the -1, which is really minus -1, which just becomes a +1. You just say +1 all squared. And now you see that the only thing missing in your formula is just your a. So to find a, if you could fill in numbers for x and y, because that's also x, then you would have a. So it means that you need a point, because a point is the only thing that will have x and y like that. So let's look and see, did they give us a point? Well, the graph looks empty, but if you look at the formula they gave you, do you see that they gave you a y-intercept? The only thing without x, your constant, is your y-intercept, and that's -5. So that's a point. So it means on your y-axis, this graph intersects the y-axis at -5. So the coordinates of that would be 0 as your x value and -5 as your y value. That's what we're going to substitute into this equation. So we're going to go ahead and substitute 0 and -5 in place of x and y. So that makes that -5 is equal to a times, and in place of x, 0 minus 5, and then 0 plus 1, all squared. Let's simplify. We have -5 is equal to, we have a. Let me actually just simplify on screen. 0 minus 5 is -5. 0 plus 1 is 1. 1 squared is 1. So you have -5 times 1, which is -5. And so to solve for a, you would divide both sides by that -5, and you see that a is finally equal to 1. Now that you have a, you can take a and substitute it into the part of the equation that was almost complete. So we're going to substitute it there. So that is, but I'm going to call this f of x because it is f of x. F of x is equal to, in place of a, we say 1 times x minus 5 times x plus 1 squared. Now, 1 times anything stays the same. So I can actually just pretend that 1 is not there. It multiplied. So f of x is equal to, we're going to leave this x minus 5 and then distribute that. Remember, that can be expressed as x plus 1 times x plus 1. That's what that squared is. So you could distribute the traditional way, or you could just do this. You look at the first term, you square that. That's x squared. Then you say first term times second term gives us x, and you multiply that by 2. So you get positive 2x. Then lastly, take the last term and square it, which will give you positive 1. And now we can distribute. So f of x is equal to, you say x times x squared, which gives you x cubed, x multiplied by 2x, which gives you positive 2x squared, x multiplied by positive 1 gives you positive x. Negative 5 times x squared is negative 5x squared. Negative 5 times positive 2x is negative 10x. And then negative 5 times positive 1 is negative 5. You see, end up with the same constant. So we have f of x is equal to x cubed is the only thing with a cube. Then we have positive 2x squared minus 5x squared, which gives you negative 3x squared. And then positive x minus 10x gives you negative 9x. And we have minus 5. So because they told us that f of x was equal to the ax cubed plus bx squared plus cx minus 5, it therefore means that a is 1. As you can see, the coefficient is 1. We already found a. B is negative 3. And c is negative 9, just as they have said it is. Okay, so the key thing here, I know many students struggle with this. The key thing is, look at your graph, look at what they gave you. Based on that, you're going to use a particular formula. So that's 9.1, and we finally move on to the next question. The next question, 9.2, says, calculate the value of x for which f has a local minimum value. Okay, so you have to think about the way f looks. F is that kind of graph. It's a cubic function with a positive a value. So that's what we have there. The local minimum, okay, would just be the lowest turning point. So that's your local minimum. So you see what they're actually asking you for. Calculate the value of x for which f has a local minimum. You just have to find the x value of your local minimum, okay, of that turning point. So let's go ahead and do that. We're going to have to try to find the turning point first. That's what we're going to do. So take the function of f, which we now know, just rewrite it. And now that we have our function of x, we're going to find the turning point since we're looking for the local minimum. So we're going to derive this function, f prime of x is equal to, and so that's going to give you 3x squared and minus 6x and minus 9. And now that you have that, to find the local minimum, you're going to make the gradient equal to 0, because the logic behind that is that when you have turning points, you see, it's all about gradients. We're looking at that. Here, the gradient is positive because this part of the graph is increasing. Then the gradient stands still. The gradient is 0 at this point. It's stationary. That's why these are stationary points. Then the gradient starts to get lower. It starts becoming negative, right? So these gradients are negative because this part of the graphs, they're really just decreasing. Then it reaches a point where it stands still and then goes up, okay? So at the stationary point, your gradient is stationary, it's 0. So we're going to say 0 is equal to 3x squared minus 6x minus 9. Okay, so just a bit of algebra here. Just going to go ahead and divide both sides by 3 since it's common all through. So we have 0 is equal to x squared minus 2x minus 3. Okay, so let's go ahead and factorize that. 0 is equal to, open up two brackets, we have x times x. And then factors of negative 3, they can give you 2. Why don't you just try negative 3 plus 1? That gives you negative 2, and if you multiply, it gives you negative 3. So x is therefore equal to 3, or x is equal to negative 1. So how do we know which one is our local minimum? Well, we know our graph looks like this. So the minimum is this one. As you can see, this would be an x value that is bigger than, let's just call that b. It's going to be an x value that is bigger than the x value here. So you know that you're supposed to take the bigger one. So just take, you know that it's going to be 3. So I'll cancel the negative one. Just in this scenario, I'm canceling it. And I'm saying that the x value for where we have a local minimum is where x is equal to 3. And that is our answer. Moving on to the next question. Question 9.3 says, use the graph to determine the values of x for which f double prime of x multiplied by f of x is greater than 0. So let's go ahead and get the graphs first. So if this is our graph, and they're specifically speaking about f of x, which is the one we have, and f double prime of x, let us just go ahead and find out what this one is going to look like. So in order to get to that, this is what happens. When you have your cubic function and you derive your cubic function, you end up with a parabola. Because this cubic function's a value was 1, meaning it's a value greater than 0, you have a cubic function that kind of looks like a capital letter N, okay? It's just more curved. If it's negative, it will look like a backwards N, okay? Just more curved. So because we have that, and because a was positive here, when you derive it and get a parabola, your parabola will also be concave up. But I want you to see how the parabola would look. It looks like that. But what actually happens is you see, I didn't draw it so well. Let me actually just try to put it right, like here, right? What happens is the x-intercept of these parabola would have the same x value as the turning point of your cubic function. So that turning point here, it would be the same x-intercept. That's why I said I didn't draw this so well. So I think it should be fine like that. So that same one should be that. But please notice that this parabola is when you derive f. So this is f prime. So what does f double prime look like? If you derive a parabola, you get a straight line. Because your parabola was concave up, your straight line is going to be an increasing function, but we need to at least know where it's going to be. So the thing about this parabola is the turning point of your parabola, the x value of that turning point is going to be the same x value as your point of inflection of your cubic function. Okay, that point of inflection. Now, here's the thing about the point of inflection. That x value of the point of inflection, so they're just speaking about the x values, is going to be the x value of your x-intercept of your straight line. This is f double prime of x. Okay, that's what it looks like. And that's how you know what it looks like. So you can kind of already look at the function and start drawing it in your head, and you can kind of see what it looks like. But of course, they expect you to, sketch it with a pencil so that you can find out what to do. So I only did that so that you know where this comes from. Okay, that we know how to get that now. That's the x value of the point of inflection of your cubic function. So I'm going to erase the parabola one because we don't really need that. Okay, I think this part is necessary. And now we can think about what we need to do. So because they say f double prime of x multiplied by f of x must be greater than 0. So the straight line times the cubic must be greater than 0. On your graph, the only way you can find this is, please note that when they say f double prime of x, they're referring to the y values of that graph and the y values of this graph. When you multiply them, they must give you something positive. The only way that's possible, okay, if you multiply two things and get a positive number, is if the two things are both positive or they're both negative. That's the only way that that's possible. So in other words, what you're looking for in these graphs is you're looking for places where the graph has negative values, both negative values or both positive values. And we can go ahead and search. Remember, you can use your trusty vertical line. Okay, hold on to your vertical line and let's look. So when we start off here, we know that of course this graph continues going down like that. And so it has a negative value, right? And at the same time, the cubic function as well. Let me actually just start from here. So it has a negative value. The cubic function also has a negative value. They're both negative here. That's one of the scenarios. Let's see. They keep being both negative. See that point? If that's a coordinate, that has a negative y value. This one also a negative y value. Okay, keep going. They both still have negative. And then here, something changes here. The reason I say something changes here is because Think about the cubic function. What is the y value this cubic function has here? It's 0. Okay, so not negative, 0. And here this one has a negative. So we'll keep that in mind. So it does not happen where x is equal to negative 1. We keep going. See that point over there has a negative y value. The y value of the straight line, negative y value. Keeps happening, keeps going, still negative, both negative. And then you get to here. At this point, they have, the straight line has a y value of 0, right? And this has a negative y value. And now after that, look what happens. The straight line has a positive y value and the cubic function has a negative. We don't want that. We want them to both be both negative or both positive. So let's pause and actually just take the ones that we just found so long. So long, we found that this, we have both negative y values here. So here on that graph, and for this same x value, it's going to be, it's going to be for this part. But you need to remember not to include negative 1, because at negative 1, that y value is 0. If you take a y value of 0 and multiply it by the y value of negative whatever that is, you get 0 and not a positive number. Okay, that's not what they asked for. So we can see that it's working all the way here. So what are the x values for which it's working for? All these values, all of their x values are values that lie here. These are values that are less than negative 1. So I'm going to say that. I'm going to tell them that x is, well, I'm going to need to change that a little bit. The reason why I'm saying so is because you see that if we keep going, it also worked here. It stopped working like here, right? It also worked here because they both have negative y values here. See, for here and here, they both have negative y values. So I'm going to find a way to sum this up. What we can actually say is we need to find that x value first because we don't know what that is. We can see that it's working for values that are less than this, but of course not equal to negative 1. So let's go ahead and find that point of inflection, the x value. We only have to find the x value. So why don't we just use the derived function that we already have and then derive that further. Then we will find the point of inflection, the x value of the point of inflection of our cubic function. So when we derive this, we get f double prime of x is equal to, that gives you 6x minus 6. Then make that equal to 0 to find the point of inflection. You have 6x minus 6. Just take your negative 6 over, equal to 6x, divide both sides by 6, and therefore x is equal to 1. So we know our point of inflection now. And so now that we know that, we can answer them. See the highlighted parts, that's all the places that it's working. We're going to say that x is less than 1, but x is not equal to negative 1, because at negative 1, that doesn't work out, okay? That has a y value of 0, that has a negative y value. When you multiply them, they don't give you something positive, they give you 0. So there we say x is less than 1, but x is not equal to negative 1. We got that part. Let's keep seeing places that it's also going to work. So let's take our vertical line, and so you would use a ruler, of course. Take our vertical line and keep looking. So here we saw it didn't work because that has a y value of 0, that has a negative y value. Keep moving. This has a positive y value, that has a negative y value. That's not going to work. Positive times negative is negative, not positive. We're looking for where it's going to be positive. Keep going. So positive and negative, and it keeps doing that until you get to 5. At 5, the cubic function has a y value of 0. And at 5, the straight line has a positive y value because it keeps shooting up, right? And so after 5, do you see that the cubic function has a positive y value? And at the same time, for the same x value, this straight line will also have a positive y value. So positive times positive is a positive number. That's actually working out. So we can see that it starts to work from here onwards as well. Here. And of course, if that graph continued going, like after 5, it shoots up. So it works there where x is what than 5? X is greater than 5. Okay, so we're going to say that Or really how I can just put it is, instead of saying or x is greater than 5, it looks weird like that. What you can just say is x is less than 1 or x is greater than 5, then tell them but x must not be equal to -1. And that would be your answer for that question. So with graph interpretation, you just have to be very careful to make sure you are looking at the graph and looking at it thoroughly to make sure that you did get everything that it's working for and everything that it's not working for. Okay, so that is 9.3. We finally move on to the next question. Okay, 9.4 says, for which values of t will the graph of p of x is equal to f of x plus t have two distinct positive roots and one negative root? So this one, it's still graph interpretation, but it's more like graph manipulation, okay? Because you're going to have to manipulate this graph, move it with drawings and stuff to see how you can achieve these roots they're asking for. Please note that they said, for which values of t, okay, so solving for t this time, will the graph of p of x is equal to f of x plus t. So this is a new graph when we're adding t, have two distinct positive roots and one negative root. So you know you can't use delta here because we're working with a cubic function, one. And secondly, they're asking for very specific roots. When they start asking for things like positive and negative roots, you can't really use delta for that. Delta doesn't manipulate roots to that extent. So we need our graph. Let me go ahead and get our graph. And when we have our graph, they asked for, and I'm glad, not that it wouldn't have worked if it was negative, but I'm glad it is positive because it's just simpler when it's positive, okay? So I'm glad that t is positive. So f of x plus t will have two distinct positive roots and one negative root. Let's look at the roots that it has right now. Right now, it has only two roots, right? One is negative and one is positive. We needed to have three roots, but specifically three roots where two are positive, one is negative. So I'm going to draw an outline of this graph so I can properly move it up or down just so that we can see what is happening in this graph. Okay, so this is the outline that I drew, and we are going to go ahead and move this. So because we have plus t, t can just be anything. We're just going to think about what it should be. Are we moving it up? Are we moving it down? Let's go ahead and try moving it down. If you took this graph, you moved it down. Look at what happens. See the issue here? No roots here, and you only have one root. So clearly moving it down is not an option. We need to move it up. So moving it back to its original position. If you move it up, what happens? Okay, so let's just move it up just by a little bit. So if it went just beyond it being at the x-axis, you see now that what you would have is you have one root there, another, and another. Three roots. But the thing is we want two positive roots, one negative. Now you have two negative roots, two negative x-intercepts, and one positive. That's not what we want. So you would have to keep moving it up to see how that works. If you keep moving it up, let's say we move it to here. And this is a very important point because you say that after moving it from this point, right, where it is touching the x and the y-axis at the same time, if you move it beyond this, that's when you actually see one negative root and there's a positive and a positive root. So this is a very important key point here. What happened here? So you see that if we move it to here, right, if you just move it a little beyond this, that's when you start getting the roots you're looking for. So how must we move it for it to look like that? Think about this. We moved it to a point where the y and the x-intercept are both at 0. Before, the y-intercept was at what? We already knew that number. It was at -5, and you moved it to the point where the y-intercept was at 0. So how far up did you move it? How many units up did you move it? If this is -5, you must have moved it 5 units up so that it can land here. Okay, so that's a key point we're going to put there. Then I'm just going to copy this graph and actually put the proper one that we're supposed to have. Let's just change the color of it. We can change it to blue. Okay, so this is still our graph, still moving it. So now when you move it up, yes, now we finally have one negative root and two positive roots. So now we know that if you move it anything more than 5 units, you're going to have your negative root and your two positive roots. That's great. But must we just move it more than 5 units and just let it continue moving up more than 5? You can just continue shooting up more than 5 units. No, we can't do that, because at some point if you do that, it's only going to have, because that's going to extend down, it's only going to have one root and then nothing there. So it means that now you need to tell it where to stop. That's what we're really doing with this graph. So we know we need to move it up more than 5 units, but how far up? Okay, and let's just see. Let's move the graph and see what happens there. Okay, so for this, I created a green graph. So if I just kept moving it up and up and up and up, what happens? Still has the roots I'm looking for, negative and positive and positive, negative and positive and positive, until I get here. What happens when I get here is that I don't have 3 roots anymore. I have 2 roots. Do you see the key things we need to look at? We should not move it past this point. But how do we know how high that is? Because I know I must move it more than 5 units, but how much should I not move it past? Well, you can find out that by looking at what the y value was here, right? And when you moved it up to that green point, what is that y value now? That y value will be 0. So you just have to find out what exactly this y value is, and you tell them that you should not move it anything more than that amount of units. Because if it, for example, was like -9, right? Then it means that if you move it 9 units up, then your graph is going to sit like the green graph, and you shouldn't move it anything more than that. So another thing is we need to find that. So this was the local minimum. Let's find the y value of the local minimum. So now it makes sense that they asked us for the x value of that local minimum. We have the x value, we'll find the y value. So let's substitute 3 into that equation. So I'll put that calculation down. We'll say f of 3 is equal to 3 to the power of 3 minus 3 times 3 all squared minus 9 times 3 minus 5. And let's find that answer. And that number is much further than I thought it would be. It's f of 3 is actually equal to -32. So now we know that number. Okay, so that calculation, I'll leave it down there. It's going to be very helpful. So now I know that number there is -32. So we should move it more than 5 units. Anything more than 5 units would give you a negative root and 2 positive roots, but nothing more than 32 units. Because when you move it more than 32 units, when you move it 32 units exactly, you can only have 2 intercepts. And if you move it anything further than that, you only have 1 x-intercept. So how we would write the values of t is like this. T should be bigger than 5. It should be more than 5, but it must be less than 32. Move it anything more than 5 units, but nothing more than 32 units. And that's your answer. Okay, so that is the last question for question 9. Then we finally